Okay, in this video, I want to look at a problem where we're looking at the temperature dependency. So we're changing the temperature. So let's look at a problem here. So we're going to consider this reaction. So we're given our reaction, and we're told that the rate constant at 701 Kelvin is 2.57 reciprocal molarity reciprocal seconds. And that at 895 Kelvin, it's 567 reciprocal molarity reciprocal seconds. And we're asked to find the activation energy in units of kilojoules per mole. Okay, so again, a lot of these problems is recognition of what we're doing, what we're looking at. So here, we're changing the temperature. Okay, so we can't use rate laws or integrated rate laws because we don't have one rate constant, right? The rate constant is going to be different at different temperatures. So anytime we're looking at a change in temperature kind of thing, we're going to be looking at our Arrhenius equation. Another giveaway to that is we're asked to find the activation energy. The Arrhenius equation is where we have an equation that involves the activation energy. So what do we know from the problem? Well, first of all, we know two temperatures. We know the rate constant at both of those temperatures. Okay. Now, you might remember the Arrhenius equation that we're typically given looks like this. So this equation is fine, but this equation is typically not the equation that we're going to use to solve a lot of problems. Now, we could if we're given the right information. So if we were given, the frequency factor and we were given a temperature and a rate constant, so we could take, say T1 here, and we could find the activation energy, right? Of course, we would have to know A here to do that, but we could do that. We could find the activation energy. But more commonly, we're going to use what we wrote as the two-point equation for the Arrhenius, right? So we looked at a graphical approach where we measured the rate constant at a bunch of different temperatures, and we could plot it out, and we could graphically analyze it. But that data is really hard to generate, and so a lot of the times when we're doing calculations, especially predictive calculations and, looking at analysis, we're going to just use a simplified two-point equation where we're just looking at two temperatures. And one of the common uses of that is to find the activation energy. So if we know the rate constant at two different temperatures, we can use that to find the activation energy. Now, of course, we could also do problems where we find one of these temperatures, we find one of these rate constants if we already know the activation energy. But this is a common type of problem that we see. So like all problems, right, it's just a matter of knowing what you know, plugging it in, and solving it. So notice we have K2 and K1. So we plug in our two rate constants and like this. So we have our activation energy here, what we're trying to find. We have R, so remember the appropriate version of R with the right units, joules per mole Kelvin. And we have our temperature. Now make sure we get the right temperature in the right place. So it's T1 minus T2. So K1 is on the bottom, so that goes with T1. K2 is on the top, that goes with T2. So make sure we get the right temperatures in the right places. So first we can solve what's in the parentheses. So we get our value. Notice the units, reciprocal Kelvin. So both of these are divided by Kelvin, so 1 over Kelvin. So now we have this. So we got to get activation energy by itself. So we can solve the left-hand side of the equation. So divide these two, get an answer, take the natural log, and we get 5.4. Notice there's no units here because the units would have canceled out. So now it's just a little bit of rearrangement. So we can divide both sides by 3.09 times 10 to the negative 4. So bring it over here. We can then multiply both sides by 8.314. So that cancels both of them out on the right side, brings them over to the left side. So we have 5.4 times 8.314 joules per mole Kelvin divided by 3.09 times 10 to the negative 4 Kelvin to the minus 1. So with a lot of these problems, the units becomes a really big deal. And a lot of times the units are a little bit complex. So what we have to think about is how do our units flow? So we have division by Kelvin up here, division by Kelvin down here. So our Kelvins cancel out. So we're left with joules per mole as our units. So do the math. We get 1.45 times 10 to the 5th joules per mole. We were asked to do it in kilojoules. So we simply divide by 1,000, 1.5 times 10 to the 2nd kilojoules per mole. Now notice I also reduced it down to two significant figures to answer the problem. Now, you would have been perfectly fine in this particular problem using three significant figures. I think I just rounded it here, but 1.45 times 10 to the 2nd would be, very appropriate here as well. Okay, so this is a pretty typical problem to find the activation energy. So the activation energy here is basically 145 kilojoules per mole. Now, a follow-up to that might be something like the following. So now you know the activation energy. What is the rate constant at a third temperature? So what if we're at 525 Kelvin? What happens? Well, we're going to do the same approach, and we're going to compare 525 to something that we know. So we're going to pick one of these other two. Now, it doesn't really matter which one you pick, but I chose to pick 701 Kelvin. So again, we have our two-point equation. So we have our 2.57. So this is our 701, right? So this is going to be our T2. So we put our K2 here. We have our T2 here, 701. So we have K1, which goes with our T1, right? And our new temperature is 525 that we're trying to figure out. Okay, so again, we're going to solve our temperature part. We get our answer with reciprocal kelvins. Now we know the activation energy, right? 1.45 times 10 to the 5th joules per mole. Now, notice I use joules per mole, not kilojoules. Why that? Well, because notice our gas constant is in joules per mole Kelvin. So our joules per mole here is going to cancel out. We have Kelvin times reciprocal Kelvin. Those cancel out. So we had to know everything on the right-hand side, so we can get that down to a number. Notice it's unitless. On the left-hand side of the equation, we have, again, we need to find something inside of a natural log. So what do we have to do? We have to take the anti-log, or the inverse log, to get rid of the natural log. So if I take the exponential of this, or e to the x, now, we're just doing some mathematical rearrangements, so taking the exponent cancels out the logs, and we simply get back what we were taking the log of, so 2.57 over K1. Now, of course, we all have to take the e to the x of the other side as well, so e to the 8.314 equals 4.09 times 10 to the third. So now here it's just a matter of solving for K1 now. So we have to do a little algebra. I brought K1, multiplied both sides by K1, brought it over here. divide both sides by 4.09 times 10 to the third. Over here, now we have our math. Notice there's no units here, so the units aren't going to change. So we get our K1 equals 6.28 times 10 to the negative 4, reciprocal molarity, reciprocal seconds. So we have our new rate constant. So notice what's happened to the rate constant, right? Compared to 701, right? The rate constant has gotten smaller. So what we're seeing here is the temperature gets lower, the rate constant gets smaller, right? Not surprisingly, right? If we think about our rate law, right? As that constant gets smaller, the rate's going to get slower, which is what we would expect at lower temperatures. So hopefully this problem gives you some more examples, some things you can look at to follow through as you're trying to do some of these problems working with the Arrhenius equation.